Welcome to lecture today. Thanks for being here, you guys. It's been a long week. A lot of stat, 1450 this week. Glad you guys are finishing it out. Looks like we have a smaller group today. Just a few quick announcements, I guess. We're going to finish up chapter 12 today and get started on chapter 11. And your exams, I think, have been graded, and those will be posted on Carmen by the end of the weekend. So stay tuned for that. That's coming soon. I don't think I have any other announcements. Any other questions you guys have or can think of, or everything going all right? Yeah? All right. Need to get my pen and flip this around. All right. Well, if you guys remember, we were talking about, we introduced this in chapter 10, talking about what probability is, and last time we started on chapter 12, some more general rules of probability. So we're going to finish this chapter off today. And just to remind you what we've talked about so far, again, in this chapter we have a bunch of general rules for probabilities. So the first general rule that we had was our general addition rule. This is always true. So for any two events that you're interested in, probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we subtract that off because we have the double counting issue going on there. This is all review from last time. Secondly, we have the complement rule, which kind of intuitively just says that the probability that something doesn't occur is equal to 1 minus the probability that it does occur. That was our second sort of general rule, always true. Thirdly, we had this conditional probability rule. If we want the probability that something occurs given that something else has occurred. So the conditional probability of B given A is equal to the probability that they both happen divided by the probability of what's being conditioned upon. So whatever comes to the right of that vertical bar goes in the denominator. That's our third one. And fourthly, we can use that to shuffle around and get a general rule for the probability of one event and another event occurring. And so, again, if you write out probability of B given A and B divided by the probability of A, you can kind of shuffle that around and get the general formula there. And then we discussed if those events A and B are independent, then we get this simplification, that probability of A and B is equal to the multiplication of the individual probabilities. So those are the four main rules that you need to have down from this chapter, and all of your homework problems will be some variation of those rules, although it can be tricky. So we're going to look at a few more examples today, introduce a few more concepts, and hopefully get you guys prepared to do your homework problems, which will be posted at some point. Stay tuned for that. So we talked about Venn diagrams so here's where we left off, I believe. We talked about Venn diagrams last time as a way of kind of visualizing events and what the probabilities of each of those events are. Tree diagrams are another thing that can be helpful, so I want to introduce and show you what this looks like. So again, going back to the blood donor example that we looked at the end of class on Wednesday, we went ahead and calculated this probability that two unrelated people are selected at random, and that the probability that they both have O negative blood. We worked through that example, and so now we want to construct a tree diagram here. So let me show you what I mean by this. So again, we have two people, and we want to know about the probabilities of each of their blood types. So the tree diagram helps us see all the possible outcomes, kind of like giving our sample space here for this problem. So first we want to split this into our first person, and then there's going to be a few options there, and we can split each one of those options into what the second person is going to have. So let me fill these in. So the first person can either have O negative blood or not O negative blood. We're going to lump all those other cases in one thing there. And then so the second person then can also have either one of those options. So if the first person has O negative, the second person can have O negative blood or not O negative blood. And similarly, if the first person has something other than O negative blood, the second person can have either option as well. And then we can fill in what our probabilities are here. Let me get a different color. So again, the probability that the first person has O negative blood from the example was 0.39, and the probability that they don't have O negative blood is 1 minus 0.39, or 0.61. So let's put probabilities in blue. And then so then what goes on the second line of this thing is the probability that the first thing occurred and the second thing occurred. So again, the individual probability that the second person has O negative blood is 0.39, same as the first person. But what is the probability of getting up to this one? So that means that the first person had O negative blood and the second person had O negative blood. And that's what we did in the example last time, right? So again, we're saying these people are unrelated. We've selected them at random, so we thought about them being independent. So if you and I have been selected at random, what my blood type is doesn't have any relation to what your blood type is. So we can use that we can use the multiplication rule where we can using independent events. So this is going to be 0.39 times 0.39. which I believe is 0.1521. So I just have the probability of the first person getting O negative blood, and then I multiply onto that the second person's chance of having O negative blood. Similarly, if the second person has O negative blood, same kind of a thing. So we want the probability that the first person has O negative and the second person does not have O negative blood. So similar, the first person was 0.39. Probability that the second person does not have O negative blood is 0.61. And that, if you calculate that out, will be 0.2379. So just kind of writing out exactly how we get to each one of these options at the end of my tree over there. So again, then dropping down to the bottom, if our first person has something other than O negative blood, that's a 61.61% of the time that happens, or 61%, excuse me. Again, if the first person has not O negative blood and the second person does, that's just like the previous option. That's 0.39. Sorry, that would be 0.61 times 0.39. Again, 0.2379. And I think you're getting the idea. The last option we have down there is first person has something other than O negative blood, and the second person has something other than O negative blood. So that's going to be 0.61 times 0.61, which is 0.3721. And again, we can use that multiplication rule because we're assuming that our first person and our second person are independent. So these are independent. So this is what a tree diagram looks like. Again, helpful when you have sort of two people here, or two stages or something like that, to kind of break down exactly what the options are and how we get to those probabilities. And then a way, if you're making one of these yourself, a way to check if you've done it correctly is if all the probabilities add up to 1. So if I take 0.1521 plus 0.2379 plus 0.2379 plus 0.3721, that should give me 1, plus or minus some rounding error, I guess. Because you think about it, if I have two people, they have to have some combination of blood types. Something has to happen. is the issue there. So is this making sense? Any question you guys can think of on tree diagrams or what we're looking at here? Yeah.
Will we only be asked to draw a tree diagram for independent variables?
Will you only be asked to draw a tree diagram for independent variables? Ah, right. So not necessarily. You might be asked to do it otherwise, but if they're not independent, then you have to be given more information. So if this was all the information you got, if they weren't independent, you couldn't do anything really. And that's a great point in that independence. We talked about it briefly. That's often something we have to assume, and we assume that when we have two unrelated people or people selected at random or something like that. If you don't assume that, then again you have to use this other rule that we looked at. If you don't have independent events, you have to use that first thing there, and often if you're not given that information, then you can't do anything. So that's another maybe tip for when you should assume independence is when you only have a small amount of information. Great question though, yeah. Okay, otherwise? So let's see if they weren't. Oh no. All right, here we go. So again, if you don't have independent events, then to get to that second probability, it's an and probability. It's probably the first thing and the second one. So if you don't have independence, you'll need to use that general rule. So you take the probability of the first thing happening times the probability of the second thing, given that the first thing happened. So that would be kind of how you would get to that and probability at the end there. All right. Hopefully that's the end of that. And then just finally in this chapter here, wanted to draw the connection again back to chapter 6. So kind of what we can do in chapter 12 here with probabilities is the exact same thing that we did in chapter 6. We can talk about them a little bit differently, but same idea. So let's do an example here where we have survey results. We have adults were asked recently whether they favored a law that would provide more support for higher education, and then we also asked each person whether or not they voted in the last election. So we classified. So here's our first categorical variable, and then here is our second categorical variable. So again, two-way table, usual setup here. We cross-classify people by if they are likely to vote in the next election and what they think about this new law here. Is there a question just came in? The blue wheel of death is asking a question. That's kind of crazy. Is there a way to mathematically determine if variables are independent? And the answer is yes, absolutely. And that will be right. That will be right here. So if the probability of A and B equals the probability of A times B, kind of goes both ways. So if they're independent, you can use that formula, and if that formula is true, then they are also independent. So, great question. You can also use that to show that something is independent, and we will do so actually in a little bit. Great question. All right. Anyway, so here's our setup. Again, we can, before we ask questions like what percentage of people are such and such, and now we can talk more about probabilities. So let me write. All right. So this first question: what is the probability that a randomly selected adult from this survey is likely to vote and favors the law? So first thing let's do is save ourselves some time, set up some notation. Let's let L equal likely to vote, and let's F equals favors the law. So what in our notation? So I'm going to put a P with parentheses. What event am I interested in here in my symbols? Say a little louder. L and F, exactly. We want the probability that a person is likely to vote and favors the new law. So L and F. And now, and I guess if you add all these up, there's 1,000 total people in there, I think. I think that is correct. So again, if I want this probability, it's going to be out of 1,000 people because I I'm just looking at a randomly selected adult from the survey, so that's out of everybody. How many of those people are likely to vote and favor the new law? Everybody said, or nobody said. Likely to vote and favors the new law. 372, exactly right. So just like before we talked about a percentage, now we're talking about a probability. We just find all those people in our table who are in the likely to vote row and in the favor column. All right, so we could write out what that is if we want. It's 0.372. Next question, what is the probability that a randomly selected adult from the survey is not likely to vote or is undecided? So again, let's let not likely to vote, let's let that be a capital N, and let's let undecided be a U. So what is the probability that I'm interested in here in my symbols? N or U, exactly right. So I want probability of being not likely to vote or undecided. So N or U. And so we did this problem before. Again, we have to add up all the row that we want and the column that we want and subtract off. But again, we can use our general rule here again. So this is the probability of N plus the probability of U minus the probability of N and U, and we'll get the same answer. But just thinking about this in our new framework here, and again, there's 1,000 total people here. So what is the probability of not being likely to vote? Well, we have to add that up, right? So the probability of N is, you take 151 plus 103 plus 25 divided by 1,000. Again, we're talking about a probability of a randomly selected adult from the survey. So again, we're talking about everybody here. It's probably of not being likely to vote, probably being undecided. What two numbers do I want to add up there? Yeah, 87 and 25. Again, those are all of my undecided people over here. And then what about the probability that I'm not likely to vote and undecided? 25. I think I hear that quietly out there. So that's, again, that will get you to the exact same thing that we saw before, but just kind of recognizing we can use our general rule here to get to that number. And if you add all those up, you'll get to 0.279 plus 0.112 minus 0.025. And the answer there is 0.366. All right, so very similar to what we have done before, just kind of putting it into our new framework of probability here. All right, I think we have a couple more questions in this example. Thirdly here, what is the probability that a randomly selected person who is likely to vote favors the new law? So again, let's let this equal capital L and favors the new law be a capital F. So what probability do I want here? Again, the probability that a randomly selected person who is likely to vote favors the new law. So what kind of a probability will this be? Kind of before we get there. Conditional, exactly. So we're assuming that we have a person who's likely to vote, and then we want to know what's the probability that they will favor the new law. So there's going to be a conditional probability. Put a little bar there in our probability parentheses there. And so then what am I assuming is true? Yeah, I'm assuming that I have someone who's likely to vote. So does the L go on the left or on the right? On the right, yes, exactly. So Again, this is what goes here is what we're assuming. It's what we're assuming to be true. So given that a person is likely to vote, what's the probability that they favor the new law? So P-F with the bar L, we can read that again, probability of F given L. So given that L happened. And again, now we have already kind of reasoned through a question like this back in chapter 6, but let's again write out what our rules here tell us to do. So again, we know this is the probability of F and L. And then which probability goes on the bottom? L, exactly. So we want the probability out of those people who are likely to vote. So that's our, kind of think about that as being our new denominator. So what we can do here is this is equal to probability being F and L. We found that in the part A. So that's 372 out of 1,000. And then the probability of being likely to vote, again, I think we, I guess we didn't actually add that up, but that would be all the people in this first row here. So 372 plus 262 plus 87, and that is equal to 721. So the probability of being likely to vote, again, out of everybody in the table is 721 out of 1,000. And then if you simplify that, that comes down to 372 out of 721, or 0.5156. Okay, everyone okay with the conditional probability there? Again, if you think about how we did it before, we kind of thought about, whatever our group of interest is went in the denominator, right? So we had kind of whoever we were interested in. Here we're looking at the probability of a randomly selected person being likely to vote. So all the people who are likely to vote, that becomes our new denominator. That becomes our new denominator here. And so then we kind of just zoom in on that row and kind of assume that the other part doesn't happen. How many of those people are likely to vote or favor the vote, excuse me. And again, we get 372 out of those 721. So kind of the way we did it back in chapter 6 gives us the exact same answer. Just kind of just putting this into our new framework here. Is that okay what I'm doing here? Is any questions you guys can think of? Okay. Finally, our last question here, and here this goes back to the question that came in just a moment ago. Is there a way to mathematically determine if variables are independent? And so we have the question that we want to know is, are the events likely to vote? So this is L and F. We want to know if those things are independent. So again, what I said in that previous slide was if the probability of A and B equals the probability of A times the probability of B. If that's true, then we have independent events. But we also had one other thing that we looked at. That was if the probability of A equals the probability of A given B. So if either of these two things are true, then A and B are independent. So again, I think the first one, the probability of A and B comes from the second fact there. And think about what that means. So if I'm assuming that the event B has occurred, and then I want to know what's the probability that A has also occurred. If that's the same as the probability of A occurring, kind of without thinking about what was going on with B, then that kind of gets at the idea that these two things are unrelated. So given that I know some information about B, if that doesn't change the probability of A happening, think about that kind of means that we have things that are unrelated here. So whenever you're asked to answer a question like this, so are these two things independent, and we have a two-way table, if you have a lot of information at your disposal, this is how we can mathematically show if two variables are independent, if either one of those things are true. And there's a few ways to do this. So let's start with the second one here. Again, we had the probability of favoring the vote. We found that to be. So again, if we want the probability of favoring the vote, we can just kind of look at those two cells of people there. That's equal to 372 plus 151 divided by 1,000, which is 523 out of 1,000, or 0.523. So I'm doing the second one first because of what we just calculated on the previous page. So here we found that the probability of F given L is equal to 0.5156. So let's write that down again. Probability of F given L, 0.5156. So is 0.523 equal to 0.5156? No, they're not equal. So they are close, but not equal. So what does that tell me about these two events, F and L? What's the answer to our question here? Are they independent, or are they not independent? Not independent, right? So the second thing that we wrote down there, this condition failed. So the probability of A is not equal to the probability of A given B. So therefore not independent. So there's our way to mathematically show. And again, there would be more than this. Is not the only way to answer this question. So we could also use our first identity up there, and we know that the probability of L and F, again, that's equal to so just our 372 out of 1,000, or 0.372. And then over here, the probability of L times the probability of F. If you work that out, it's 0.721 times 0.523. Sorry, I'm running out of space here. And that is equal to 0.377. So again, it's close, but not equal. So that would be a way of showing, again, these things are not independent. Yeah. Great question. So if we tested the first one and they were equal, for example, would you also have to test the second one? Technically, yes, but I don't think we'll ask you to do that. No, the rule, to show that they are formally independent, you would have to check all the possible options there. But that's tedious. So we won't ask you to do that. So if you can find one thing where they're equal, that's okay. Yeah. Yeah. So is this not close enough to being equal? Is that your question? Yeah. So take it out 3 or 4 decimal points when you're looking at probabilities. And again, try to save your rounding until you get to the end, just sort of for good practice. Again, I think, well, if, for example, on a homework or on a test, if you did round and got them to be equal to each other, you might lose a little credit. But if you said they're equal, so therefore they're independent, so kind of if you know what that means, that's the important thing. So just justify what you get. Yeah. So again, most times independence is something we assume is true. So again, we take randomly selected people or unrelated people. But when we have a two-way table like this and lots of information, we can find these probabilities and show that they are equal or not equal. Yeah. And so I think that brings us to the end of chapter 12. Any final questions on 12 you guys can think of, or is this all making sense? So as we've been introducing this this material, I think you'll find the homework problems. I don't know which exact ones are being assigned yet, but they can be much more tricky than the ones we've looked at in class here. So what I will do is I think I have an extra example worked out. Instead of kind of going through it now, I'm going to post that on Carmen and just give you something to look through because these problems can be a lot more complicated. So stay tuned for that. I'll have that up maybe over the weekend here. Everything okay on chapter 12? Yeah. I don't know. I'm not sure when the homework is going to be due, the next homework assignment. That information is still coming out. Sorry about that. I will talk to Dr. Baker and see if we can get that out today, whether it is or is not due. Okay, in that case, we're going to take a step backwards and going back to chapter 11. So chapters 10 and 12 are related. Not quite sure why the textbook puts them in this order, but I think this is a little bit more of a natural ordering here. And we're going to talk about something called sampling distributions. So hopefully you guys were able to find those notes. I emailed them out to you yesterday, sort of late. And they're also posted on Carmen under the supplemental materials for this lecture. Okay, so again, this slide, we saw this at the beginning of chapter 12. Just to remind you again, we started, first part of the course was chapters 1 through 9, essentially. We looked at probability, and now we're ready to move on to that next step. So now is kind of when we're getting into the real statistics part of this course. So what we want to do is we want to take information from a sample and generalize it to our population of interest. So we talked a lot about finding a sample, getting a random sample, collecting information from them, how to do that well. And now we're going to start talking about how we actually use that information to say something about the population that we're interested in. So the key idea here was that, again, if I take a simple random sample of Ohio State students and ask them a survey question and then look at the proportion who say one thing or another, and then you take a simple random sample of students from Ohio State, our samples are almost definitely going to be different, right? So you take a simple random sample, I take a simple random sample. We have different people in those samples. So that's this idea that samples vary. And so what we're going to talk about in this chapter is kind of quantifying the variation that we get in our samples and describe how the things that we can calculate from those samples, how they behave. And in general, we're going to use sample statistics to estimate population parameters. So actually, let me come back to this. Let me scratch out this for example right now and give you some definitions here of what I mean by statistic and parameter. I think I have these in the wrong order. So again, we've talked about difference between population and sample, right? The population is who we're interested in. The sample is people who we actually collect information from. So there was that one problem on the exam review where it was like we sent out a survey to 250,000 people, and we got responses back from 240,000 of them. Who was our sample? And the sample was the people who actually responded. So the people in your sample, you have to actually get information from. It's kind of the important difference. And again, remembering the population, we're not going to be gathering information from everyone in our population. That usually would take way too long. So then what I have here is the definition of a parameter and a statistic. So again, a parameter corresponds to the population, kind of a P and P there, and a statistic corresponds to the sample. And so a parameter is, here the definition is, it's a number that describes a characteristic of the population. So for example,
maybe that's the mean debt after graduation for Ohio State students. So again, whatever my population is, if it's all Ohio State students, some characteristic of that is what I mean by a parameter. And then the exact value of that parameter is in general going to be unknown, because we're not talking to the entire population saying what is your debt after you graduate from college, all of these things. So we're saying that number is unknown in theory. Whereas a statistic is sort of the corresponding thing that we can calculate from our sample. So again, we collect information. We take a sample of Ohio State students. We ask them what their average debt, what their debt was, and then we can compute the average from that group. So again, for example, this would be like the mean debt if we took a simple random sample of 400 students. So parameter corresponds to the population, and that's unknown. A statistic corresponds to the sample, and that's something that we actually can calculate. So using the information that we collect, then we can compute that statistic. So a few examples here of what I mean by these things, and this kind of reminds you of our notation. So these two things up here, mu and sigma, these are our parameters. So again, we've talked about this a lot. We've said that mu is going to correspond to our population mean. That's like the overall mean for whatever our population is. And sigma is going to be our population standard deviation. So it's kind of the standard deviation of our population. And so up until this point in the class, we've often said assume that the population is normal with mean this and standard deviation the other thing. So that's we've assumed that we knew them, and now we'll kind of go back and say, well, how did we get there? So in general, that mu and sigma are not going to be known here. So kind of draw a line here, and these numbers down here are our statistics. And by statistic, I just mean that that's something I can calculate from the data. So I have my sample mean, my sample standard deviation. Again, if I have 20 people, I can calculate their average height or their average whatever. Or I can also calculate standard deviation of whatever I'm looking at. So again, those are things that I can calculate with the information that I have. So statistic corresponds to the sample. Parameter corresponds to the population. Just keep that in mind. And so again, kind of the natural idea here is we will use too many L's. We will use X bar to estimate mu. So again, the line right above the definition says we will use sample statistics to estimate population parameters. Kind of the natural idea. If we want to know what the population mean is, we can use our sample mean. And similarly, we will use, I can't write today, can I? We will use S to estimate sigma. So kind of using the corresponding sample quantity to estimate the population quantity. All right, everybody okay on my notation here and kind of what I mean, statistic, parameter, population, sample? All right. So again, keeping in mind that we want to do this second thing here. We want to use these things to estimate something about our population. So if we want to estimate the population mean, we're going to use the sample mean. And so what I've said here is that the sample mean is a random variable. So thinking back to chapter 10, what I mean by a random variable is a quantity what was my definition of random variable? This is the outcome of a random phenomenon. So remember, a random variable is the outcome of a random phenomenon. So going back to that coin toss example, that's an example of a random phenomenon because I can flip the coin. I don't know exactly what I'm going to get, but random variable will be some outcome of that. So just like that, if I take a sample, I don't know exactly what the sample mean is going to be. Right? It could be a bunch of different things. And so what we learned back in chapter 10 and 12 was that each random variable has a distribution. So we had a probability model for our random phenomena. Same thing. We have a distribution that tells us what values that random variable can take, and then the probability that it takes on those values. So again, x bar is a random variable. And it will have a distribution. All right, so where are we going here? So if you remember back to that example we looked at in chapter 10 when we were looking at the probability that the student was exactly 7 minutes early or whatever it was to class, that probability was equal to 0. So same kind of an idea here. The paradox is that the probability that the sample mean is exactly equal to the population mean is going to be 0. But nonetheless, we expect that sample mean will be somewhere close to the population mean. So it might not be exactly on it, but it should be close. And that's what I mean by that is that it's the sample mean is unbiased for the population mean. So x bar is unbiased for estimating mu. And what I mean by that is this: we expect it to be close. We don't expect it to be a whole lot bigger or a whole lot smaller. We shouldn't over or underestimate the population mean. And then kind of thinking back to that random rectangles activity you guys did in your recitation. I think you guys all did that. We talked about the idea that the average of everybody in our classroom. So if we each took our average of 10 blocks from the random rectangles and we found an average. We had an idea that the average from the whole class in general would be closer than any one of the particular averages. And that's kind of the same idea. So as our sample gets bigger and bigger, we would expect our estimate to get better and better. So as we take more individuals from the population, we would expect the sample mean to get closer and closer. So in general, it should be close, but the estimate will get better if we have more people in our sample. And this is what we mean by a law of large numbers. So this is a term thrown around. I feel like often I'll hear sports commentators say something about the law of large numbers. I feel like they often get it wrong. But in any case, what we're talking about here is that if we're taking observations at random from any population, so if we're taking people from our population and figuring out what their or whatever it is that we're interested in, what their debt is after college or something like that, as we start averaging more and more people together, so as our number of observations increases, as our sample gets larger, the mean of the observed value should get closer and closer to the population. Kind of just saying in a formal statement what we just said on that previous slide. That's what I mean by a law of large numbers. So as the numbers get bigger, we should get closer to what we want. And then you can check out your textbook there for a little example and graphic. I'll forgo that for now. So thinking about it in another way, the law of large numbers says that if we sample enough people, so if our sample size is big enough, then x bar will eventually get close to the unknown value of the population parameter of mu. So typically we just take one sample, right? We don't actually take more and more people in our sample and hope it gets closer and closer. Typically we just have simple random sample of 100 or 30 or 86. And so we can't, in practice, we're not going to be able to just keep sampling more and more people until we get closer and closer. But this is the idea of what we want to do and what we what we'll use that for is to, if we get a good idea of what the behavior of X bar is. So if we can understand how X bar behaves, then we can get a better idea of this. So two distributions that I want to introduce here, this notion of a population distribution and a sampling distribution. And we'll use these to kind of understand how X bar behaves. So the population distribution, again, is the distribution of the values of the variable among all the individuals in the population. So this would be the, for example, the distribution of everybody's average debt here at Ohio State. And my sampling distribution here is of a statistic, so of say X bar. Sampling mean of a statistic could be the sample mean, could be something else. Tells me the distribution of values taken by the statistic in all possible samples of a certain size from that population. So for a particular sample size, it gives me the values that random variable takes on for all possible samples. So population distribution sort of corresponds to everybody in my population. Sampling distribution talks about the distribution of my sample mean or whatever I'm interested in at the moment. So just, okay, so again, the population distribution talks about individuals. So again, population, if I'm thinking about average debt or something, I'm talking about individual people. Those are the values that I have. Whereas the sampling distribution is values of the sample mean. That's calculated from samples of some size. So that's kind of, again, this is probably a little vague at this point. I think I have a picture here to show you. Okay, so suppose I have, suppose this is these 400 students, suppose these are my population. So this is one of those cases where, and this is not in your notes. So this is one of those cases where the population, excuse me, is not that big, and I sort of in a theoretical case, I have collected information on everybody. So I have my subjects, I have my 400 subjects, and I have their height. And again, you know, I have this sort of bimodal thing going on. I have women and men in here, obviously. So this would be an example of the population distribution because I just have the heights of my 400 students in my histogram here. So again, each number that's going into that histogram represents an individual. But suppose now that I take 1,000 simple random samples of size 5. So maybe not all of them, but I take one simple random sample of size 5. So that's my first one, and I have 5 people in that sample, and I compute the average height. I can do that a second time. I can take another simple random sample of size 5. I have those three numbers in the 5 numbers in the second sample, and I can calculate their average. I can do that a whole bunch of times. And then what I can do is I can take these numbers here, and I can make a histogram of them over here. So now what's down here is the average from a, well, simple random sample of 5. So this now is a sampling distribution because this is the distribution of that sample average that I have there. So I'll come back to this example, but just to kind of put this picture up here is that the population distribution has individual people in it, and the sampling distribution, I take a bunch of simple random samples, I calculate those sample means, and so on there. So population distribution, sampling distribution, and I'll come back to this example, I think, later in this chapter. So this is kind of a weird concept. Is this making sense? You guys have any questions you can think of? Yeah. Mm. Yeah, right. So the question, the comment was, do we not lose our shape here? So we go from our population distribution has one shape. It's kind of this bimodal thing going on here. It's very very clearly bimodal. We kind of have those two groups in there. But yeah, like Sarah said, we would just have kind of a unimodal thing going on over here in our sampling distribution. Absolutely. So that is the exact idea that we'll be building on later. So yes, the shape of the distribution will change, and that is a very key idea. So these distributions will not look the same, and that's kind of the important thing that we'll use later. So excellent observation. Okay, well again, I think examples will sort of start to help show you what I'm talking about here. Oh my goodness, I'm out of time. That was fast. Maybe this is probably a good place to stop. So we'll talk more about what I mean by these two things next week. Thank you guys so much for being here. Have a good weekend. Hopefully we'll have some information to you out about the homework very soon.